Recording in progress.
All right, morning everybody. Please, the usual story, shut your laptops, pull out your name tags just so, I still don't remember your names. And there we go. Thank you. So, all right, we're going to continue with our series on recurrent neural networks. I'll wait for you to settle down, all of you guys. The attendance poll is 1271, right? The class is hopefully empty. We actually had, I did Monday on Zoom in part because I figured people would still be creaking in from spring break, number one. And number two, that several of you would actually miss the class if I had it in person because your body clock is probably not adjusted to daylight savings. Well, it's 2 days later, and I'm expecting that everybody is awake and that you can actually make it to class. So it's a bit disappointing that the class is empty. Anyway, let's start, right? So here's the problem we've been looking at. Using recurrent networks for analyzing time series and generating time series. But then what we are actually doing when we do this is to convert sequences to sequences. Some sequence of inputs x1 through xn goes in, and a different sequence y1 through ym comes out. So this was what we had in speech recognition, right? The sequence that came out had a different length than the sequence that went in. So different examples, speech recognition, speech goes in, transcription comes out, machine translation. English goes in, German comes out. A dialogue system. I pose a query, a response comes out. Question answering. I pose a question, an answer comes out. Your language models. The large language models that all of you have definitely been poking around with. What goes in and what comes out may not be the same length at all. But the general problem is one of conversion of one sequence to another. So here, we can look at two kinds of problems. The first one, which we've been looking at, is the one on top, like speech recognition, where you have a speech signal going in and this transcription coming out. The other one is like machine translation, where you have English going in and German coming out. The two are fundamentally different. Now, in the second case, which we will not be dealing with till next week, observe that there's no clear correspondence between the input and the output. I ate an apple, goes in one order. The German that comes out, the order of words is very different. There's no one-to-one map. In fact, if this were a dialogue system, what comes out would have nothing at all to do with what went in. For the specific kind of problem, like, my screen is blank, would be the signal, would be the text going in. The output is, please check if your computer is plugged in. No relation, right? But the kind of problem we are working with is this one, which has a very specific characteristic. Namely that the input and the output are order aligned. What I mean by this is that the order in which the output symbols happen, firstly, the output symbols are going to be fewer than the input. And the order in which the output symbols happen corresponds to the order of the input, which means that the first output symbol corresponds to the initial portion of the input. The second output symbol corresponds to the second portion of the input, and so on, which is why you can actually align the outputs to the input. So this is what I will call time asynchronous, because you don't have a one-to-one correspondence between our input and output, but order synchronous outputs, right? Conversion. Now, the issue we saw over here is how do we perform inference in such a model, how to output time asynchronous sequences. And the second is how do we train such models, because as we saw in the last class, there's no clear one-to-one correspondence, right? So how do we perform inference on these models? That we saw, but let's look at how we can train. For training, we saw that if you were given an alignment where you were told exactly where in the input each of at what instant of the input each of the outputs must happen, then we could actually just replicate the symbols to fill up the entire sequence, so that now the problem has been converted to one of a time-synchronous conversion, where there's an output corresponding to each input. And then we could always write out the divergence between the target and the input sequences, which is going to be the sum over all time of the Kullback-Leibler divergence between the desired and actual outputs. And the KL divergence, as we saw, when we represent the desired output as a one-hot vector, this is simply the negative of the log likelihood assigned to the correct symbol. And you can see why this divergence makes sense, that you're minimizing this loss is going to be maximizing the probability of the correct symbol at each time. And of course, the way once we had this kind of an alignment, the way we actually performed gradient descent was to start off by computing the gradient of the divergence with respect to every single input, every single output produced by the network. And the derivative of the divergence with respect to any given yt, we saw, was simply going to be a vector of all zeros with just a -1 over a non-zero term at one component, and that one component corresponds to the target symbol, and the value is minus of 1 over the probability assigned to the target symbol. We saw all of this in the last class. The big issue was, how do we train when such alignment is not provided? And so all that's given to you is the sequence of symbols for the timing information. Where does each symbol occur? That has not been provided. And here we saw that one possible solution is to actually iteratively estimate the alignment, meaning you'd initialize your model somehow, use that model to align the input, align the target output to the input, and then once you'd aligned it, you could actually use these aligned sequences to update the model, and then you could use the updated model to go back and realign the inputs, realign the target outputs. And this works. This was what the process of alignment was, what we call the Viterbi alignment algorithm. And training, of course, is the conventional problem of training a recurrent network. Yes?
You have like if we take the example that you give, like 50, which is like 4 out of 20 or 3 out of 27 of the 4 names. But then how do we initialize those 3-4 names out of the 27?
So we said we'd initialize the alignment. So for example, if I have a recording which is 10 vectors long, and I have beefy, which is 4 symbols, then I could just quite arbitrarily decide that the first quarter corresponds to the B, the second quarter of the input corresponds to E, the third quarter corresponds to the F, and the fourth to the next T.
But that is given that we know Wi-Fi exists in those 10.
So this is, you're given the transcriptions, right? So when I'm giving you the audio recording and the transcription, that's the label sequence.
So our objective is to identify the phonemes. We know what phonemes.
This is for training. Right? For training, you're assuming that you actually have the information, right? Any more? Fasten. Okay. We're going to be calling out names again. There's a guy called Lavender Falcon, or girl called Lavender Falcon. Who's Lavender Falcon?
Hi, I am.
Okay. What's the answer to the first question?
I think it's true.
Thank you. And there's a falcon of another color, green falcon. What's the answer to the second question, green falcon? Is green falcon online? No? Okay. Teal leopard. Who's T leopard? T leopard is missing.
I may be a letter, I don't remember the name. That's the color.
All right, that's okay. I'll let you answer. What's the answer to the second one?
I think it's true.
It's true. Thank you. Right? So both of them are true. Viterbi training explicitly estimates the alignment for each training instance and computes the divergence of the estimated alignment. And thank you, Clifford. And it requires re-estimation of the alignments in every iteration, right? This is what we saw. The problem here is that, now this is about training, right? We're not really speaking of inference. I'm given a collection of recordings, a collection of data, input sequences, and the output order-aligned sequences. How do I train my model? And to train the model, if I had the alignment, gradient descent is easy. If I'm guessing the alignment, then I have a problem, right? Can you shut your laptop there? Thank you. Right, so, and the reason is that the act of guessing can be noisy, particularly when in the initial stages of training, when the model is really poor, you're going to come up with very poor alignments, and this can lead the model into going into very poor local optima, so you end up with bad models. What is the workaround for this? You don't actually want to commit to an alignment. The problem lies with committing to an alignment that could be wrong. So let's not commit to an alignment. This is what we're going to do. Instead of trying to guess an alignment, we're going to use every possible alignment of the symbol sequence to the input. And how would we do this? For this, let's go back and look at how we actually perform the alignment in the first place. Remember, if I was trying to align B phi to the input, the first thing I did was to create this reduced probability table, where each row corresponded to one of the symbols in my label sequence, right? And then subsequently, any path through this table which started from the top left corner and went to the bottom right corner and followed the rule that the path could either go forward or diagonally by one step represented a valid alignment of the symbol sequence to the input. Any single path over here is going to represent an alignment of B phi to the input in my example. And the path itself in our iterative estimation algorithm was the one that gave us the best alignment of the symbol sequence to the input using our current model. And by best, we meant the most probable alignment. So once again, when I'm speaking of the most probable alignment, what this really means is that there is a probability distribution across all alignments. So for example, over here, I could have, something like that. That's one alignment, right? I could have something like this. I could have any number of alignments. And corresponding to every one of these alignments, there's going to be some probability, 0.001, 0.0001, whatever. And we pick the most likely alignment. We just happen to have an algorithm, an efficient algorithm, to find the most likely alignment. So I can think of this as there being a probability distribution over all alignments, where each of these is one of these alignments. And what I did was to choose the alignment that was most probable, and I used that for my training. So selecting a single, this is the same as drawing a sample from my distribution of alignments, except instead of random sampling, I'm picking the most likely alignment. Now, once I think of it this way, here's a second way of looking at it. That corresponding to every one of these alignments is a probability, right? Let me assume that all alignments are possible, but each with a different probability. In that case, instead of just considering my loss with respect to my, most probable alignment, instead I can replace this with the expected loss over all alignments, where I look over all, where the expectation is over the probability distribution over alignments, namely this guy over here, right? If I can compute this, then I'm not committing to any single alignment. I'm considering all possible alignments. That makes sense to you guys? Right? And so that's what we're going to do. We're going to be considering, we're taking the expectation of the loss over all possible alignments. But then, for any given alignment, the loss is simply the negative of the sum over all time instants of the loss at the individual instant, right? So this over here so if I had my network produce probability vectors at each time instant, then I would have, for any alignment, I'm going to be considering the sum of the losses at the individual instance, and then I'm going to be summing them up. And so that's simply going to be minus of the sum over all time of the log of the probability assigned to the symbol assigned to time t by the alignment. And this is what I'm going to be taking an expectation of. This is the loss I want to minimize if I'm not committing to any single alignment. But then the law of linearity of expectation means that, well, even before that, here's the second point. You didn't see the answer, guys. Okay, this is an easy one. The next one is emerald seal. Okay, just released? Sorry. Okay, we'll give you 15 seconds. It's easy, since you can see the questions. So emerald seal, who's emerald seal? There is no emerald seal in class. Okay, we'll keep the color. Emerald woodpecker. That's true. Thank you. And the second one, bronze turtle. Who's bronze turtle? There is no bronze turtle in class.
True.
Oh, true. Thank you. Thank you, bronze turtle. So here you go. Training without alignment computes the average divergence over all possible alignments of the label sequence to the input. But then, does this actually require explicit alignment estimation of the alignment of the label sequence to the input? If I'm computing the average divergence or the expected divergence over all possible alignments, this means that I don't actually ever estimate an alignment, right? Because I'm considering every possible alignment. I'm not picking a unique alignment. And so the second one is false. Now, how do I compute this expected divergence over all possible alignments? So what I'm trying to do is to compute the expectation of this term, which is the sum over all time of the log probability assigned to the symbol in the alignment, minus of the sum. And using the linearity of expectation, this E can go inside. So what happens now is that I'm summing over all time, but at each time, I'm computing the expected loss at that time. So what is this loss over here, this second term? let's take a look. When I want to compute my alignment, the very first thing I did was to construct a graph, right? And so I had a table, which maybe I had my beefy example. And then I had these, and then I had fur, and then E again, right? And I constructed the entire graph in this manner. So this term over here is the expected, now corresponding to every one of these boxes, there was a probability. So the box over here was the probability that the symbol at time 0, 1, 2, 3 was F, right? And so each of these boxes has correspondingly log probability, right? In this case, it's going to be Y3B. This would be log of Y3E, and so on, right? So every one of these boxes has a log probability. What is the average of these log probabilities? That is this expectation that we're taking. But then it's not just a regular average. It's an expectation, which means that you have to consider the probability of the box itself. So what I really want to do over here is to say, what is the probability that the true alignment went through this box times the log probability assigned to that box, right? Plus what, again, times the negative of the log probability assigned to that box. Plus, what is the probability that the true alignment went through this box times the negative log probability assigned to that box. Plus, what is the probability that the true alignment went through this box? So you'd go down the column at each time, and at each time, you're computing the probability that the true alignment went through that box, meaning this one over here is the probability that the time 2 actually aligns to E, and that is the probability that you multiply with the log probability of the symbol within that node, within that box. And then you're summing this over the entire column. That makes sense to you guys? Right? So the question is then, how do we compute this probability? This is the probability that of aligning a specific symbol S at time t, given the input and given the compressed sequence, right? So we need to be able to compute this term. And what exactly is that term? Now let me look at this box, this graph again. So for this term over here, this probability is the probability that the third symbol, for example, so for example, it's the probability that the third input aligns to E, right? And the probability that the third, now, yes, because the probabilities within the boxes have been computed by the network. You're assuming that you're given a current network that you're going to be updating after estimating these probabilities, right? And so here, what is the probability that this box aligns to the input? Now, or lies within the alignment. Now, observe that the alignment must go through one of these 4 boxes. So if you summed up the probabilities of the 4 boxes, they must sum to 1, right? But what's the probability that the second box is going to be the correct alignment? That is going to be the proportional to, that's going to be the sum, proportional to the sum of the probabilities of all paths through the graph that go through that node. In other words, the probability that the third input aligns to E is going to be proportional to the probability of the graph, subgraph, shown by the blue arrows. It's the set of all paths that go through the third node. That makes sense? Right? And why did I say proportional? Because what we actually compute in the graph is going to be the probability, is the joint probability of the symbol sequence and the input. Whereas, well, let me get to that in the next slide. Let's look at this figure over here, right? So what we really want is the probability of this subportion of the graph. If I compute the probability of this subportion of the graph, it's going to tell me something about what is the probability of aligning the third input to the symbol E. And now the probability of this subgraph shown in pink is the probability that the input corresponds to B phi and the third input corresponds to the symbol E. So the probability of the subgraph is this joint probability of the symbol sequence and the specific event of the third input corresponding to the symbol E. Whereas what we really want is the conditional probability of the third symbol being E given that this input corresponds to B phi. Let's set that aside for now, right? Let's focus on how we can actually compute the probability of the subgraph shown in pink. How would I do that? This subgraph shown in pink has two parts. The lead portion of the graph that starts from the top left node and goes into this box, right? And the second portion of the graph, which starts immediately after the blue box and goes all the way to the end, to the bottom right node. So does decomposition make sense, right? And so now I can write the probability of this graph, which again is the total probability of all alignments which align 3 to E. That probability can be thought of as the probability of the portion of the graph encircled in blue times the probability of, it's actually the, write it out fully. It's going to be the probability of the blue subgraph and the red subgraph given X, right? Which I can write as the probability of the blue subgraph given X times the probability of the red subgraph given the blue and the X. The first half and the second half, simple Bayes rule, right? But then here we realize something, right? The blue subgraph is the total probability of all alignments that align the third input to E. The red subgraph represents all alignments that align the third. So the blue subgraph is the total probability, is the set of all alignments that align the first three inputs such that the first symbol is B and the last symbol is E, right? The blue subgraph is the set of all alignments that align the rest of the input to the region starting from E to the final E, right? But then if I look at the probabilities of these two things, the probability for the red subgraph and the probability for the blue subgraph are entirely different, are entirely independent given the input. Why so? So if you look at how the network computes probabilities, at any time, if you have the hidden states, and if you compute the set of output probabilities at each time, does this probability directly influence the next probability in any way? Does it? Yes or no?
If you're considering the first
Think about this. I've already given you the input, right? So once the input is given, these things are deterministic. So whether this probability is 0.3 or 0.4 has no influence in what's happening over here. That information is entirely within the hidden state of the network, right? The only manner in which something over here can influence the next probability is if I actually drew some value from this sample and fed it back to the input. So long as I'm not actually drawing a sample from time t to feed it back to the network at time t plus 1, then if I've given the input, the computation is deterministic. The probabilities are all computed at each time are all independent of one another. So given this, then you have this so-called conditional independence because the inputs govern the hidden state, and the hidden state governs the probabilities. So I can simply decompose this probability as the probability of the pink graph times the probability of the blue graph, right? And so I'm going to call the first term, the probability of the pink graph, the forward probability. It's the total probability of all alignments that are for the initial portion of the sequence that end up aligning the third symbol in this case to, the third input in this case to the symbol E. I'm going to call the second term, the portion that's in blue, the backward probability, which is the portion of the graph that starts off with aligning the third symbol, the third input to the symbol E, and aligns the rest of the input to the remaining portion of the label sequence. So the forward probability will be represented using the symbol alpha, standard notation, and the backward probability is beta. So given this, the probability of the entire graph is going to be such that the tth input is aligned to the rth symbol. It's going to be alpha tr times beta tr. Yes?
On the naming convention, why is the blue part backward?
We will see. Right. So let's see how we're going to compute this forward probability first, right? This forward probability is going to be the total probability of this subgraph over here, which is the portion of the graph that starts at y0b and ends at y3e. Now, what are the ways in which I can end up at y3e? There are only two ways, right? I can end up at y3e either from the red node or from the green node. So the total probability of y3e of the portion of the graph that ends at y3e is going to be the probability of this subgraph times the probability of extending it by the additional symbol plus the probability of this subgraph times the probability of extending it by this or the new symbol. Make sense, right? And what is this guy over here? What is the probability of this subgraph? Anyone? Yeah.
Probability of the first two in that subgraph.
But symbolically, right? What would that be? That's just an alpha, correct? So the probability of this, so just as the probability of the subgraph that ends at 3e is alpha 3e, the probability of the subgraph that ends here is going to be alpha 2b, right? And so the probability of this event, this subgraph and then extending it by the symbol e at time 3 is going to be alpha 2e times alpha 2b times y3e. So also this guy here, what is the probability of the subgraph that ends at this point? That's going to be alpha 2e, right? And so the probability of this graph here is going to be alpha 2e times y3e, right? So that makes sense to everybody? So the overall probability of the graph, subgraph that ends here is going to be the sum over all parents of this node of the product of the alpha for the parent times the probability of the symbol itself, the probability of the node. That makes sense to everybody? Very simple, right? If you look at the picture. And so I can basically write this entire the probability of the alpha probability for any node in this manner. The alpha probability for any node is the sum over all the parents of the node of the alpha for the parent times the probability of the node itself. Everyone with me? Once I have this, I can compute the alphas for the entire graph. It's very simple, right? So here's what I can actually pull out the common term. So alpha TR is the sum of alpha TR is the sum of alpha T minus 1R, which is the alpha here, and alpha T minus 1 R minus 1, which is the alpha here. The whole thing multiplied by the node probability, which is YT symbol SI. That's just the notation, but it's basically stating in symbols what we just said. And once we have figured this out, we can compute the alphas for the entire graph, for every node in the graph. I can start at the leftmost node, and I know that the first node must be the top left node. So the probabilities for all the other nodes in the first column of the subgraph are 0, right? And for the top left node, it's just going to be the probability assigned to that node. In this case, it's going to be Y0B. Then I can go forward one step, and then I can use this formula that we just had, which was, where is this term here, and compute the alphas for all the nodes in the graph, right? Because at each point, again, remember that the alpha at any time is basically computed using the alphas at time t minus 1. So I can use the alpha at time 0 to compute the alphas at time 1. Then I can, now that I've got the alphas for all the nodes at time 1, I can use them to compute the alphas at time 2. And I can use those to compute the alphas at time 3 and so on until I've computed the alphas for the entire graph. So I'm going from the beginning to the end. I'd have to start off at time 0 and then work my way forward till I've computed the alphas for every node in the graph. But I'm going left to right, so this is a forward propagation of probabilities, which is why we call it the forward probability. But the general algorithm makes sense to all of you, right? And you should be able to code it up. So what is the alpha at the final node, the bottom right node? The alpha at the bottom right node is the total probability of the entire graph. That is going to be the probability that the symbol sequence B-phi can be aligned to the input. It's the total probability of every possible alignment of B-phi to the input. Make sense? Okay. So, can you shut your laptop properly, please? Yeah. It's very uncomfortable to see you lean back and look into it. Okay. So now, so we've computed alpha TR for the entire node, for every node in the graph. We've seen how to compute this. So this is done. What we need to do now is figure out how I can compute the probability of the subgraph of the blue subgraph. Now that you've seen how you can compute the probability for the red subgraph, does that give you an idea of how you can do this? How you can do this for the blue subgraph? You can just flip the graph left to right, right? And repeat the whole process, and it's going to be exactly the same algorithm. But then let me do it slightly differently. Let me start at the end and work my way backwards. So this is the probability of the blue subgraph. It excludes the orange node because the blue subgraph, as you saw over here, doesn't actually have that orange node, right? It's the probability of the subgraph starting from the orange node, but not including the orange node. But just for convenience sake, so this is what I'm going to call beta TR. It's the beta TR is the probability of the subgraph starting from the TRth node, but not including the TRth node. Okay. Now, just to make things convenient, I'm going to include the orange node in the computation. And that will give me the probability of this entire subgraph, including this node. But then once I've done computing the probability, I'll just divide by the probability of the node and get rid of that probability. So I just have the probability that I actually want. So now let's see how I can compute the probability for the graph that I've just shown, the exposed portion of the graph. So the probability of, now if you consider this subgraph here, when I start from Y3, from 3E, that node has only two children, the green child and the red child. So the total probability for this PR is going to be the probability for this subgraph. I can follow Y3, 3E by 4E and then take one of the many paths that follow, or I can follow 3E by 4F and take one of the many paths that follow, right? So the probability of the graph to the top left is going to be the sum of the probabilities of the two pictures shown below it, right? That makes sense? That is this term. So I'm calling this beta hat 3E, right? Because I put the hat to indicate the fact that I've also included the source node, okay? So beta hat 3E is going to be the probability of this subgraph plus this subgraph, which is going to be the probability of Y3E multiplied by the probability of the subgraph starting at the green node, plus the probability Y3E multiplied by the probability of the subgraph following the red node. So what is the probability of this portion of the graph? Again, using the same notation. Anyone? That's just going to be, the portion of the graph starting in the green node is simply going to be the beta probability for the beta hat probability for the green node, right? The portion of the graph starting at the red node is going to be the beta hat probability for the red node. And so once again, I'm going to get beta hat 3E is Y3E times the sum of the beta hats for the children of 3E. So, yes?
Should that be beta hat 4E inside the bracket over there?
For which one here? Let's see, that's 4F, right?
Yeah, because the
Oh,
first,
so this one is 4E, I'm sorry, you're right. The first one's 4E, right? So I can generally write this as so. Beta hat TR is going to be, the probability of the node at TR times the sum of all the children of the TRth node at time t plus 1, of the sum of the beta hats for all the children of the TRth node. Does this make sense? So now it's very simple. The rest of the computation is simple. I can start off at the bottom right node, and I know the beta hat value for this bottom right node, which is simply the probability for the node. And now again, note that the betas at each column are computed using the betas at the next column, right? So I have the beta here, and I know that the betas for all the blacked out boxes got to be 0 because the final node in the path cannot be those boxes. Then I can take a step back and compute the betas for all of these nodes. Again, for each node, the beta hat value is simply going to be the sum of the betas for the children times the probability of the node itself. And I can work my way all the way back till I have got the beta hats for every single node in the graph. And now you can see why I'm calling this the backward probability. I start from the end and I work my way backwards, right, to answer your question. But then what I really wanted was the probability of the graph without the head node, right? And so I'm going to have to divide by the probability of the lead node once I've computed this entire beta hat and to actually get the beta value that I want. Make sense to everybody? So that's my code for it, okay? And so now I have found a way of computing a probability for the blue graph, which is beta TR. And so the probability of the entire graph that goes through the TRth node is going to be the product of alpha TR and beta TR. Everybody with me? Right. So, but then here's the thing. This is going to be the probability of the graph that goes through this node. that is going to be the proportional to the probability that the third input aligns to the symbol E, right? If I want to compute the actual conditional probability, given, so this is what this actually tells me, is the probability of that the entire input aligns to BFE and the third input aligns to the symbol E. So the product of the alphas and betas are simply going to be the total probability of the subgraph shown, which is the joint probability of the label sequence and the event that the third input is aligned to the symbol E. So if I want to convert this to the conditional probability, given that the input sequence is BFE, the label sequence is BFE, what is the probability that the third input is aligned to E? I'm going to have to normalize it. So what this means is that I'd compute alpha times beta for each one of these nodes. And the alpha beta, the product of alpha and beta is not this, the sum of the products of alphas and betas for all 4 nodes down the graph is not going to be 1. So I'm going to divide by the sum to make sure, to ensure that this, that these probabilities sum to 1. And that is this conditional probability that the third input in this case aligns to the symbol E, or more generally, that the Tth input aligns to the Rth symbol. That makes sense to you guys, right? And I'm going to be representing this probability by the symbol gamma Tr. So gamma Tr is going to be the normalized product of alpha and beta, but the normalization is with respect to the sum of the product down each column of the graph, right? And so now that I've got gammas, my loss, now I can compute the gammas very trivially, because the forward algorithm is a very simple algorithm. It's a dynamic programming algorithm. It's done in essentially linear time. The backward algorithm is also a simple dynamic programming algorithm. So the alphas and betas are easily computed. I can use the alphas and betas to compute the gammas. And so the divergence is simply going to be the sum over negative of the sum over all the nodes in the graph of the product of the gamma for the node and the log of the probability assigned to the node. That makes sense? We just converted it to a very simple operation. You basically got a matrix of gammas. You got a matrix of log probabilities. You performed an element-wise product and summed the lot. And the negation of that gave you the loss. Does that make sense to everybody? I can see you guys falling asleep, but still. So, because if it didn't, you have a problem. Yeah.
Not overcount certain parts.
Doesn't, right? You just saw.
I get that when we're summing it over the column, it's fine, but when we sum it like across columns as well.
So the expectation is over all possible alignments, right? Yeah. So it's going to be we just saw it's going to be the sum over all time of the expectation at each time. So that basically just gives you the probability.
Because my concern is that like when you're looking at the path for like 3E or 4F, they could have the same path, but we're counting it twice when we're summing up over the different time steps.
So when you're computing the probability for 3E, that is the probability of aligning the third input to E, right? It must consider everything before.
Okay.
That's all. Okay. There's only one question. Who's Silver Rabbit? There's no Silver Rabbit. And who's Scarlet Turtle? There's no Scarlet Turtle. Who's the Purple Owl?
That's me.
Okay, what's the answer?
I believe it's the second one.
Both of them are true, right? So the forward-backward algorithm is used to compute the a posteriori probability of aligning each symbol aligning in the compressed sequence to each input, right? The entire graph, every node in the graph. And these are required to compute the expected divergence across all alignments of the graph, because you're summing over all the nodes, and the term you're summing is the product of the gamma and the negative log likelihood, right? So once you've done that, then I have my divergence defined. And once I have my divergence defined, I can actually compute the derivative of the divergence with respect to the output of output of the network at each time. Now again, we have to remember that when I computed this divergence, I did two things. My network gave me an output at, these were my inputs, and my network gave me an output probability vector at each time. And what I really want to do is to compute the derivative of the divergence with respect to this vector, right? But then I took some elements from this vector and composed my reduced table. And any specific node over here might in fact occur multiple times in my graph, as we just saw. And the divergence that we computed is basically the divergence is computed over all paths through this graph. So because we've computed the divergence over all paths through this graph, I can compute this term. How much does a small perturbation of this guy change the overall divergence? That I can compute from the derivative formula, right? And so correspondingly, I can compute how much does a small perturbation of any of these terms change the divergence. Now, if there's a probability term that doesn't occur in this graph, will perturbing it change the divergence? No, right? So the only terms in the probability that will affect the divergence are the probability terms in this vector that actually appear in the graph, right? So for example, if this were B, then B occurs here. So I can compute the derivative of the total divergence with respect to this term, and that's going to give me the derivative for this guy, right? Now if this is E occurs twice, here and here. So I can compute the total derivative of the divergence with respect to this node and this node and sum them up. And that's going to give me the derivative with respect to E, right? And then once I have these derivatives, I can actually compute the derivative of the divergence with respect to the entire output of the network. So the question then becomes, how do I compute the derivative of the divergence with respect to each of the outputs of the network at any time t? So these are the terms that I must compute from this derivative formula, right? For this, for any symbol here, I have to sum over, so this is at any given time, then I just have to go over the corresponding time within the graph. I have to sum over all the nodes that include, that are copies of this particular node over here. So in my graph, for example, if I'm considering E, I'll be considering two nodes. And at each node, I'm going to be summing the derivative of the contribution of that node to the entire divergence. So that's going to be d over dy of gamma times log y, right? Very simple. And what is d over dy of gamma times log y? That is simply going to be over here. This is the term that we want, right? And this is the derivative we need. That's simply going to be gamma over y plus the derivative of gamma times log y. Everyone with me? Now this second term ends up being particularly ugly. It's going to be hard to compute. This first term is trivial. It's already given to you. So what do you do as a good engineer when something is too ugly to compute? You throw it away. And then you come up with some alternative math that explains it. And so instead of saying we're going to train gradient descent to actually minimize the expected divergence over all alignments, I can just say I'm maximizing the probability of my graph, at which point the second term disappears very magically, and the first term is trivial, right? It's just the gamma divided by y. And so, since this term is easy to compute, that gives me the ability to compute the entire derivative. So if I want the derivative with respect of the divergence with respect to the output of the network at each time, firstly, the derivative is going to be 0 for any element which doesn't appear in the graph. For the elements that do appear in the graph, I'm going to go over all the nodes where that element appears, and I'm just going to be summing up gamma divided by y over those nodes. And that sum, so basically 1 over minus 1 over y times sum of gamma, because y is common to all of those. And that is the term that's actually going to appear in this derivative formula, right? So the overall process of the training the network becomes very simple. If I'm just given the input and the output sequence without alignment, and if I must train the models, I'm going to set up a network, typically a many-layered LSTM. Then I'm going to initialize all the parameters of the network. Then I can pass my input through the network. It's going to give me a vector of probabilities at every time. Then from this vector of probabilities, I can compose the reduced table and the corresponding graph. Then I can perform the forward algorithm over it to get the alphas at every time. I can compute the backward algorithm, perform the backward algorithm to also get the betas for every node at every time. And from the alphas and the betas, I can compute the gammas, which is simply the product of alpha beta normalized over the columns. And then once I've computed the gamma, then gamma divided by y, or right, minus of gamma divided by y gave me the derivatives. And so I can now compute the derivatives, and I can just, so this gives me the derivative of the divergence with respect to the output of the network. That can now be backpropagated using standard backprop rules to train the rest of the network. That make sense to all of you guys? Right, yes.
When we have repeated symbols, why do we have to, like for the E part, the two E's that we have in MLP, why do we have to, when we compute the derivative of the divergence with respect to?
So that's because, see, the E occurs in two portions on the graph, right? So the E occurs in this node as well as in this node in my example.
So both are valid.
Yeah, because think about this. If I perturb this guy, this one influences both of these nodes, right? So I have to sum both of those nodes, and both of those nodes influence the divergence.
So at that point, it's like a shared parameter?
So you can say this node, the probability over here is being copied to both of these, right? And both of these in turn are going to influence the divergence. So if I want the derivative of the divergence with respect to this, I have to sum over both of these guys, that's all. Make sense? Okay. So far so good. So here's what we've seen so far. These sequence-to-sequence networks, which irregularly output symbols, can be aligned using Viterbi alignment. To train them, they require alignment of the output to the symbol sequence because this alignment is generally not given. And training can be performed by iteratively estimating the alignment by Viterbi decoding and time-synchronous training, or it can be performed by optimizing the expected divergence over all possible alignments, which is what we just saw. So this is all very fine, but we are still left with a problem that we alluded to in the last class and that we haven't addressed thereafter. So let's say I have an alignment which is RR, 3 E's followed by 3 R's followed by 4 E's and a D, right? Is this the word read or is this the word read? This information is not present, right? So we have a problem. If I compress this, which of these two words does it become? We saw this before, right? When we were doing the greedy decode. So we want to have the model be able to distinguish between read and read very clearly. So in order to do this, we're going to introduce another symbol to our vocabulary. This is the invisible symbol. I'm going to represent it using a blank. It's a symbol that cannot be seen, but actually does occur. So, for example, I could have this aligned sequence, 3 R's, 3 blanks, 3 E's, 3 blanks, and 3 D's. And then when I compress it, and how did we compress sequences? By just eliminating repetitions, right? So if I compress it, that's going to compress to R blank E blank D. But the blanks are not seen, right? So it's going to look like RED, right? Or this guy over here. So this one is 2 R's blank E, 2 blanks, double E and D. If I compress it, it's going to become R blank E blank ED, right? The blanks are not seen, you're going to see REED. So similarly, this one over here, 2 R's a blank, R, 3 blanks, 2 E's, 3 blanks, D blank, DD, right? If I compress it, all the repetitions are going to go away. So that's going to become R blank, E blank, D blank, D, but the blanks are not seen, so it's going to become RREDD, right? Using the same logic, what would this fourth one become? There's going to be RRREED, DD, right? So you get the idea. The blank actually exists, it just cannot be seen, okay? So, here's a problem. So that one's easy. So maybe Navy Falcon can tell me the answer. Not yet published? Why's that? Should have been published, okay. Navy Falcon is still on the hook for the answer, yes. That's you?
Sorry.
So the first one, okay, BILLY. Does everybody agree that the last one is the correct answer? Thank you. So you guys get the idea, right? Now what this means is that now I must deal with, so once I introduce this blank symbol, then this business of the ambiguity of repetition has gone away. But then now I must incorporate this in training, right? Among other things, the model will now also include the blank as an entry in its vocabulary. So now when the model actually outputs a probability table, it's going to be outputting probabilities not just for the symbols in the vocabulary, but also for the blank, right? And so if this is what it outputs, if I were to pick the most likely symbol at each time, for example, then this would be, B, 2 B's, E, 2 F's, 4 F's, and then E, right? So what would that compress to? Over here. Anyone? That's 2 over here. What would it compress to? Beefy, right? Because it's just going to be compressed. The repetitions go away. It's going to be B, E, F, and E, right? Easy. On the other hand, if my most likely outputs at each time were this one, then what is that going to compress to? It's going to be the same thing, still beefy, right? But now I have these blanks which were not seen. But what about something like this? Yeah, double F, right? So you can see, you get the idea, right? I'm changing I grumble about this example every year, but I don't change it. So I'm going to change my symbol sequence to have 2 E's in sequence, just so that you can see the issues that arise from having this blank. So when I do this, here was the graph that I actually originally had when I wanted to align my symbol sequence to the input, right? I just pulled out the rows from the table and composed the graph. But then, if I introduce blanks, something funky happens. So to understand what goes on, let's look at this figure over here. In the first example, when I had B phi, I just had B followed by E, followed by F, followed by E. So I can think of it as a linear graph, that B must always be followed by E. E must always be followed by F. F must always be followed by E. That gives me B phi. But then if I have an invisible blank, there are multiple possibilities which all look like B phi to the naked eye. I can have B followed immediately by E, and wait, so this is, I should actually have another arc over here, followed immediately by F and followed by E. Or I could also have a B followed by a blank followed by an E, right? As far as you are concerned, both of them are going to look like B followed by E, right? So I have so the simple graph on top became the uglier graph at the bottom. So for B phi, or if I have, let's say I have this guy here, versus, let me take a look at this. So if I have B phi, right? The graph for this is going to look like, so it's going to be B, F, E, F, and E. And I can have a direct connection of this kind. But then I could also have a blank, right? And any path through this graph is going to represent B phi. Everybody with me? But suppose I have something like this. Then can I still have this structure? Will any path through this graph still represent B, E, E, F? No, why not? If I don't have a dash between these two, this is going to collapse to a single E, so I'm not allowed this arrow. That makes sense to everybody? Right? And so, if you look at this table, the reduced table is going to represent, this is the sequence. I can also have a blank at the beginning and the end, right? And so the reduced table is going to look, so B phi, or in this case B, E, E, F, I can also have a blank at the beginning, which is optional. I can also have an optional blank at the end. And they're all going to be read as B, E, E, F, right? So that's what is shown vertically to the left. And so the corresponding probability table, which consists of all the rows from the table pulled out, is shown to the right, right? And now let me draw my actual graph. The graph looks like this, right? Any particular symbol can repeat. I can go from the first B to the blank following it, or I can go from the first B directly to E, right? So I'm going to have out here from this guy, horizontal arrow, I'm going from B to blank, or from B directly to E. Now from E, and from this blank, the only place I can go is to the next symbol, because obviously I cannot skip a symbol, right? That's following this graph out here. But then from E, I'm only allowed to go to the next blank and not allowed to skip. Because if I skipped, then the second E is going to get clobbered. So did the graph make sense to you guys? So I'm going to insert a blank between every two symbols. From any blank symbol, the arrow can go only one step down diagonally. From a non-blank symbol, I can either go one step down diagonally or two steps, unless the two symbols are the same, right? If I have E followed by E, then I can't skip the blank, right? That make sense to everybody? And once I represent it in this manner, then the problem of repetition is gone. The one extra thing that you see over here is that you can also have a blank at the beginning or at the end. And then you have these skips, which only occur across blanks when the symbols on either side are different, right? In general, you can say if the symbols on either side are different, you're allowed to skip, otherwise you're not, okay? And then once you do this, the rest of the algorithm remains the same. The forward algorithm is exactly the same as before. You would start from the first column. You would have alphas for the first two nodes, and then you're going to go from left to right, except that when you're going from left to right, some nodes will have two predecessors and some nodes will have three predecessors. And so when you compute the alpha at any time, the number of terms that you're going to sum over depends on which node it is. And a simple way to figure out whether you have two predecessors or three predecessors is to see if the previous visible symbol was the same symbol or not. If it was the same symbol, then there are going to be only two predecessors because you're not allowed to skip the blank. But if they're different symbols, then you're going to have three. Make sense? Right? To everybody? And so also, so these guys only occur when the two symbols on either side of the edge are different, right? And so also for the backwards. I can start off by having betas as zeros for everything except the last two nodes on the graph. And then I can work my way backwards, except that when I'm computing my beta hat, I'm summing over all the children of the current node. Sometimes a node will have two children, sometimes it will have three. And the only time it will have three is if A, it's not a blank, and B, the next symbol is not the same symbol as itself, right? Then it will have three children. So that's about it, nothing changed, right? And then the rest of the algorithm stays the same as before. This is still computing beta hat. To convert it to beta, you have to divide it by the probability of the node itself. And so posteriors and derivatives are computed exactly as before, but using the extended graph with blanks. And so the overall training procedure, you're going to have to set up your initial network somehow, initialize it, and then initialize all the parameters of the network. For each training instance, you pass the training instance through the network, and you're going to get probabilities for all the symbols, including the blank. Observe that the actual training data never explicitly gave you the blanks. Nonetheless, you are going to be able to compute the posterior probabilities for the blanks because some paths go through nodes that include blanks, right? And then once you do this, you can perform your forward pass, as we just saw, to compute the alphas for all the nodes on the graph. You can compute your backward path to compute the betas. And then finally, once you've got the alphas and betas for every node, you can multiply them and normalize them across the column to compute the gammas. And subsequently, you can compute the derivative of the divergence with respect to the output of the network at each time. And again, to compute the derivative of the divergence with respect to the output of the network, for each symbol for which the network has computed a probability, you're going to go down the column and check how many times that symbol has occurred. And you're going to sum all of those gammas and then divide by the probability to the symbol of the symbol. Then the negation of that is the contribution, right? And so that's what you've got here. Yeah.
So really with the blanks, how do we compute because they're not given and are the same for each of the blanks?
It's just a single blank, right? The blank is not given. Nonetheless, you can compute the posterior probability for the blank. Because I can compute, because the blanks are in the graph. So I can compute the alphas and the betas, correct? So I can get the gammas. And so what I would be doing here is I'd be going down each column and find all the entries where any given symbol occurred. So if it was a blank, for example, if I have a compressed symbol sequence with 4 characters, then there are going to be 5 instances of blank, right? So I'd be summing across all 5 instances of the blank. And what I would sum is the ratio of gamma to 1, right? And that's going to give me my derivatives. And once I have the derivatives, I have the derivative with respect to the output of the network, I can back propagate it to train my network. Right? This applies to models that are output order aligned, but time asynchronous outputs. So far so good. But then there's still one problem I left on the table. And that is, how do you actually perform inference with this model? And what was the problem of inference? The way we saw it earlier, we could just do a greedy decode. I could pick the most likely symbol at each time. And once I introduce blanks, that works fine, right? Because even if I compress it, there is no ambiguity of repetition. But is it the optimal thing to be doing? And we can see that the answer is probably no. Why? So let's consider this example over here. Let's say I have all of these possible alignments that I can pull out from my probability table, and I find that RR blank EED has a probability of 0.7, RR blank blank ED has a probability of 0.68, and so on. So if I were doing the greedy decode, which symbol sequence would I pick? Over here, TED, right? Because it has the highest probability. But then there are multiple alignments of red. All of them have high probability. They're just individually never the highest. Whereas in the case of TED, there's one alignment which is kind of standing out, but the rest are very poor. So considering all of these, which do you think is the better choice, red or TED? Red, right? So what we really want to be doing is considering the total probability across all alignments, not just the probability of the most likely alignment. And still, right, greedy decode would just pick TED. And as it turns out, greedy decoding actually does a pretty good job 90% of the time because of the nature of this model. What happens, this is a very nice example from the original paper on this technique. What they show is that there are these epochal events where there's a change from one symbol to the other. And those are the only times at which the probability of a symbol sticks out. At all other times, it's usually just the probability of the blank that is largest. So, the blank seems to take over the job of a nothing happened here character. And so just a greedy decode actually still manages to give you a decode where the greedy decode tends to give you an alignment which probably compresses, or with high probability compresses to the correct answer. But nonetheless, what we really want to do is to perform the optimal decode. And if I'm performing the optimal decode, I'm going to go over a couple of minutes, guys, just bear with me. What we want to do is to pick the compressed symbol sequence that has the highest probability given the input. And what is the probability of a compressed symbol sequence? How do you compute it? For any given compressed symbol sequence, you'd have to compute this, you'd have to construct this graph, and then you'd have to compute the alpha value at this bottom right corner. And that alpha value is going to give you the total probability of all alignments of the sequence to the input. And so if you wanted to perform recognition classification, you'd have to compute this alpha value for every possible sequence. How expensive is that going to be? Impossible, right? There's no easy, cheap solution to this. But then this is where engineering comes in, right? So again, the actual decoding expects us to pick the most likely compressed sequence. I'll skip there. You don't need to answer the poll, but can somebody answer the first question? The actual objective of decoding is to identify the compressed sequence that has the highest probability given the input, true or false? Guys? True, right? Right. And the second one, it's the same as finding the compressed sequence with the highest forward probability, alpha, and the final symbol, right? True or false? True. Okay, everybody say true together, please. True. Thank you, right? I know you're asleep still. So how do we compute this? I'll go over this in 3 quick minutes. The good news being you're going to have to implement it in your homework, so you learn. Okay. So here's what I'm going to do. I'm going to arrange all of my possible symbol sequences as a tree. So let's say I have only 2 symbols in my vocabulary, S1 and S2. Implicitly, I'm also going to be including a blank, right? Blank is the invisible symbol. So the first symbol can be either a blank or an S1 or an S2. All of them are valid, right? And then an S1 can be followed by an S2. And S1 can also be followed by a S1, but for an S1 to be followed by an S1, it must first be followed by a blank, right? And then an S1 followed by a blank can also be followed by an S2, right? These are the possible extensions. Now, if you look at this node here, this represents the sequence S1, right? This node represents the sequence S1, S2, regardless of the path that you took to come here. This one represents the sequence S1, S1, right? Similarly, I can draw the lower portion. S2 can be followed by S1, or S2 can be followed by a blank followed by S2, or a blank followed by S1. But once again, each node represents a unique symbol sequence. This is S2. This is S2, S1. This is S2, S2, right? And I can draw an entire tree in this manner, right? This represents every possible symbol sequence. And then I can have this tree be my vertical axis, and I can compose my graph exactly as before, where I actually, when I go across time, I'm going to draw arrows from any node to nodes at the next time instant if I've got an arrow from the node over here to those nodes in the graph, okay? And then I can just use the forward algorithm going forward. I can perform the forward algorithm going all the way to the end. When I run out of inputs, observe that every node over here represents a node here, which represents a unique symbol sequence, right? So all I have to do is to go down that column and pick the row for which the alpha was highest, and the corresponding symbol sequence is going to be my most likely answer. Except you have a problem. The tree keeps increasing in size. And so, we're going to perform beam search. So I'd expand it initially, then keep maybe just the n highest, expand only those n, keep the n highest, expand only those n, and eventually when I get to the final input, my computation is never really blown up. And then at the final input, you're going to observe that there may be up to 2 different sequences which represent the same compressed sequence. That's because, in this graph, the final node may also end up being a blank. Right, so here, this guy represents S1, this one also represents S1. You sum their 2 alphas and pick the symbol sequence for which the alpha was largest as your classification output. I'm not sure if that made a lot of sense to all of you guys, but did the rough idea come across? Yes? Okay. We're out of time. Thanks for the 3 minutes of extra patience. I'll pick up on Piazza. I'll see you next class. There's some very nice pseudocode for beam search on the web, on the slides, but there's an even nicer, very compressed pseudocode algorithm for the beam search that we just saw, which is maybe about 30 lines of Python, including headers and trailers. So we'll post that.
So you're doing divergence. Has anyone found how much it actually corrects accuracy?
I have not seen any people which use that.